Good. So where are we at? Well, this is our error function. This is called in this case, it's the one-dimensional reconstruction error. It's the error that you get by using phi1 as your basis vector. This is what's left over. And so this is actually xi minus the projection of xi onto phi1. It's what's left over. It's using phi2 through phi(n), which are unknowns. But we're going to just focus on this. We said minimizing this error was the same as maximizing this quantity. But we're going to go ahead and say we want to maximize the fraction here just to enforce the fact that we want phi to be we want phi to have unit size. Okay, and so now we're going to examine this for a bit. Good. And the easiest way to do that is to notice that C is a special matrix. It is the covariance matrix, which is symmetric. And so therefore, let V1 through Vn be orthonormal eigenvectors of C. And we're going to put these in order. These are in order so that lambda 1 is the biggest eigenvalue, lambda 2 is the next biggest, and so on, down to lambda n. So the first eigenvalue is going to be the biggest, and so that's going to correspond to V1. Lambda n is the smallest, corresponding to Vn. Okay, because these are n orthonormal vectors in Rn, right, that means that they form a basis for that space. And so we can write phi1 as C1V1 plus C2V2 plus Cn Pn, right? And in fact, like we were saying before, we already know what the constants are. But in fact, I don't think I need them right now. Let's go ahead and rewrite this in terms of the matrix vector in matrix vector form. So V1 through Vn times a vector C, right? So that's V times, oops, that's not a matrix, sorry. That is a matrix V times the vector C. I'm trying to keep the notation the same as the book. Good. So then, what is phi1 transpose C times phi1? Well, that's going to be the matrix V times the vector C transpose times the covariance matrix C times V times C, right? Good. So that's the vector C transpose matrix V transpose C times V times vector C. Good. And how would you compute this? Well, remember that C is V times lambda, I guess we could say lambda times V transpose, right? So this whole thing is the vector C transpose V transpose V lambda V transpose V C. Okay, there's a lot of V's in there. But V transpose V is just the identity. That's the identity. And so you end up with C transpose, that's C1 through Cn times lambda 1 through lambda n times C. Okay, and now how would you compute this? C1 through Cn times, now this is an n by n times an n by 1, so you're going to end up with an n by 1 vector, right? So this is lambda 1 C1 times 0, 0, 0, 0, and then 0, lambda 2 C2, and so on. So this is going to be lambda 1 C1, lambda 2 C2, lambda n Cn. And so do you see what you're going to be left with? Am I still on the screen? C1, so that's going to be lambda 1 C1 squared plus lambda 2 C2 squared plus lambda n Cn squared. Okay. Good. So this quantity right here is phi is the what's in the numerator to this, right? Let me rewrite that. I'll pause just a minute and rewrite my notes. Good. So we just showed that the numerator of our expression can be written this way. Remember, the CI squareds are the coefficients of the phi in terms of our basis for the eigenvector. The basis we're using is the set of eigenvectors of C. Okay. And then phi1 transpose phi1 is equal to the coefficient squared plus the coefficient squared. We proved that, by the way. That's, again, the Pythagorean theorem. So we won't show that again. That's pretty fast to show if you want to. But the idea here is that this quantity is showing up on the numerator and the denominator, right? And so we have, let's let rho I be equal to Ci squared divided by C1 squared plus C2 squared plus Cn squared. So P1, so what happens when I factor this out? I can take phi1 transpose phi1 C trans. Let's see if I can talk. Okay, I'm just going to write. How's that? Okay, that's going to be lambda 1 C1 squared over C1 squared plus Cn squared plus lambda 2 C2 squared over C1 squared plus Cn squared. Okay, so you see what's happening there. Oops, I forgot my lambda n. Good. And so that's equal to, I'll go ahead and write down our rows now. Lambda 1 rho 1 plus lambda 2 rho 2 plus lambda n rho n. And the important thing to notice is that each of the rho i's is greater than 0. And what's the sum of the rho i's? I equals 1 to n of rho I. What happens when you sum these together? You get 1. Therefore, this quantity right here is a weighted average of the lambda i's. Lambda i's. That doesn't, okay. Good. And this is really a critical thing here. Because what did we want to do again? We wanted to maximize this quantity. Max. And so what's the unknown in this expression? The unknown in this expression are the CIs. C1, C2, C3 up to Cn. The lambdas are the eigenvalues of C, so those are fixed, right? So it's the C's. I need to figure out what the C's are to maximize this expression, which means I need to figure out what the rows should be that maximize this expression. Good. Now think about this. Suppose I've got lambda 1 rho 1 plus lambda 2 rho 2 plus lambda n rho n, and I want to find a bigger quantity than any of these. Well, what I can do is I can just replace each of the lambdas by lambda 1. Right? Because lambda 1 is bigger, lambda 1 is bigger than lambda 2. So I can replace everything but something bigger. Lambda 1 times rho n. And notice that is equal to lambda 1 times the sum of the rows, which is equal to lambda 1. Therefore, this expression can never be bigger than lambda 1, the biggest eigenvalue of C. Let me say that again. That's really important. This expression cannot be any bigger than the biggest eigenvalue of C. Okay. When is it equal to the biggest eigenvalue of C? It's equal to the biggest when rho 1 is equal to 0. So we get a max when rho 1 equals 0. And oops, sorry, I just messed that up. Rho 1 equals 1 and the rest are 0. Now remember that phi1 was equal to C1 V1 plus Cn Vn. So if C1 is equal to 1 and the rest are equal to 0, are you ready? What is the direction that maximizes this quantity? Here it is. So V1 is the direction, or the vector, that maximizes phi1 transpose C phi1 divided by phi1 transpose phi1. Good. Oops, I ran off the page, didn't I? Are you screaming at me? Okay, there it is. We're done. That's the best direction. That's the best basis. So the best basis for a set of data, the best one-dimensional basis for a set of data, is the eigenvector of the covariance matrix corresponding to the first eigenvalue, or the biggest eigenvalue. Very good. Excellent. All right. Now, how do you get the rest of the eigenvalues? Or how do you get the rest of the basis vectors? Well, we already know that the eigenvectors, because C is symmetric, we can use the spectral theorem to say that the eigenvectors form an orthonormal basis. And so you can show that if you project out V1 from the data so that none of the data points have, all the data has a 0 direction in V1, and you just look at the remainder and find the next best basis vector, you'll find that it is V2. And then if you project out again, you'll see that the next best vector is V3, and so on and so on and so on. It actually is almost identical to this argument that we just did, except that whenever you look at this expression now, once you've gotten rid of V1, this number goes away, and so lambda 2 becomes the next best. Okay, and so it is possible, but it does take a little bit of time. And so what we end up with is the best basis theorem. So let me write that down before we stop the video. The best basis theorem. Given data x1 through xp, where xi is in Rn, the best basis is found by taking the first k eigenvectors of the covariance matrix. Okay. By the way, I didn't have k up here, so what's the k? The k can actually be anything. If you're looking for the best one-dimensional subspace, you would just use one basis vector, or one eigenvector. If you're looking for the best two-dimensional subspace, you'd let k equal 2. If you're looking for the best three-dimensional subspace, you'd let k equal 3, and so on. You hope that there's actually, at some point at which the rank of the matrix, right, would be low. And so in that case, you might actually only be able to go up to like R vectors, right? But that's not usually the case in the real world. Okay. What did we say about the first k vectors of the covariance matrix? Do you remember? How do you get those from the matrix X? Where are they? Oop. Maybe it's just faster to tell you. You can show these vectors are the left singular vectors of the SVD of X, formed by these being the columns. So, oops. So this is n by p, n by p. Very good. And by the way, these also have zero mean. You don't want to have a bunch of data that doesn't have zero mean. Otherwise, what happens is that the first eigenvector pretty much points in the direction of the mean, and so you end up removing the mean anyway. Good, that's it. In the next video,